اعمل ايه عشان اشوف الموضوع؟ بس عايز اشير السكرين كده. شير السكرين. انا مش عايز كده كويس قوي. خليك معايا يعني ده ماتر يعني. Good morning everyone. Can you hear my voice? Good morning everyone. Can you hear my voice?
Yes, I can hear you.
Okay. Thank you, Professor. Good morning, our professor. Here I am with my colleague Ahmed Fady. Today is the last day in our workshop after yesterday talk and the day before. The day before we enjoyed a lot of talk and our professor Casticadellis was with us. And I always say he is my father in boundary elements, and he is a civil engineer, by the way. Is not mechanical or mathematician or something like that. Yesterday we had a very nice talk from Professor Alex Chang also, and Professor Edward Kansa. I'm talking about boundary element guys, which I am very interested in their talk, to be honest. Today we have the last day of the workshop. We have mainly three main lectures. The first lecture, I'm going to talk with my colleague Ahmed Fady about boundary element based software called PLPAC. And we stayed developing this software over the last maybe 20 or 25 years or something like that. I can't remember. At the beginning, I believe I was talking to Professor Toshiro Matsumoto from Japan, and I told him I'm planning to develop this software, and he told me one statement I will never forget, and I have never forgotten this statement. He told me, you have to do it. Perhaps you are the only one are capable of doing something like that, because you are civil engineer and at the same time you are understanding boundary element very well. Anyway, before we start this talk, we have another talk from Professor Xing Huashin, and I believe he is very, very good professor, excellent professor in boundary elements and computational mechanics in general. He's going to talk about Traftis and fundamental solution-based finite elements. Personally, I worked with fundamental solution-based finite elements, and I have one of the guys that he worked with me and finished master and PhD, Dr. Taha Bunnaga. He did a great job in this, and we developed a new element. Actually, we use a fundamental solution as trial function inside the finite elements. And he's going to talk about Traftis method also. Traftis method use complete homogeneous solution for finite elements. And I wish we can do this in boundary elements. The last talk, it will be by my colleague, the other colleague, I think, Muhammad Kamal. He's with us here. Can you show yourself? This Muhammad Kamal, he is doing. Before I want to tell this to Professor Casticadellis, but we always accuse us in boundary elements that we couldn't solve nonlinear problems. And when we solve nonlinear problems, we use non-physical stuff. With Muhammad Kamal, we employed a Shelby inclusion theory to physically represent the nonlinear problem. Even we could be able to develop a stiffness matrix from the boundary elements, condense it direct on the boundary. And the inclusion represents the deterioration inside the domain. I will leave this to Muhammad Kamal to present it in his talk. You can say. Then we will have the closure. I guess we can start now our talk about the PLA pack, a boundary element-based software for structural engineering applications. This lecture will last a lot, to be honest. Okay, please remember to register. On our website, and I'm going to start a very long lecture. My colleague Ahmed Fady will take over to get some rest from talking, and then come back and so on. So if you can see my screen, I believe you can see my screen. Before, maybe from a long time ago, when I was doing my PhD, we always talk about when the boundary elements is going to be used in industry. And I was thinking, why we don't use software to do something like that based on boundary elements. I'm going to present a huge lecture today. This lecture is not a presentation only. It is a standalone document. I will going to leave it on the website after that, so you can, anybody interested can come back to this lecture and see all of the details. But I'm going to go very fast in this presentation. What I want to present is, okay. What I want to present here is I'm going to show you now how step by step how to start that user point. I'm sorry, this one. I'm going to show you how can we use boundary elements in solving tall buildings, including soil structure interaction. Even we put nonlinear soil structure interaction, and you can see this is the real building. This is one of the floors from the PLA pack software. We have it, and this is the model inside the PLA pack, and this is the analytical model for the vertical elements from our software. So this is our software in front of you, and you can easily replace all available finite element-based software, and you can use this software. And I'm going to show you what are the advantages of using such software. I'm not asking anybody to remove the software he is using or to replace this software by my software. No, not at all. I'm going to ask, please try to use two different software. One based on finite element, one based on the boundary element, at least to have a feeling that you are doing the right modeling stuff. We will start with a table of content. We have, as you see, 5 parts. We have 5 parts. The first part is going to talk about the basic version. The second part, we are going to talk about the design tool, because we have designed according to the Egyptian code of practice, the ACI code of practice, and the Euro code of practice. Then we will talk about, in the part 3, about the foundation package mainly. Then we are going to talk about part 4 in the post-tension package, and we are solving post-tension slabs with optimizer. You can get us, as you know, Ahmed, for example, you can get us cable profiles, and then you can optimize your profile, because post-tension slab has a very good applications in the States and in the Gulf area. Part 5, we will talk about the dynamic package and how to couple superstructure with substructure, including nonlinear soil structure applications, and we will move to link it to Navis work and demonstrate 4D and 5D for construction engineering. So you have everything actually, and I'm going to demonstrate videos showing this. I start with part 1. In the introduction, the main purpose of this software is we use the shear deformable plate bending theory. Shear deformable plate bending theory, I'm not going to say it is Resner theory. Resner theory, it is the most general theory. You can solve a thin plate, you can solve a thick plate, you can solve everything. You don't have shear locking as in finite element. You have everything in front of you. I'm going to show that this PL pack, the best thing about it is you don't have something called analytical model. You don't have analytical model. What you have is a real drawing. You change it to something we call it building information modeling model. Then you can develop your model type. As I say, I left all of that. I left all of that for any person to come back to this. Okay. We have mainly packages. The basic package, which is solve one floor. The post-tension package, solve one floor with post-tensioning. The design tool to design package, and the foundation package, would solve a foundation on piles, even with using nonlinear piles and pile-pile interaction, pile-soil interaction. We have dynamic package. If we couple these packages together, we'll get tall building over fixed base. If we couple the foundation package with the fixed base, we get the overall package. The basic package, I'm going to talk about the one floor only one floor. We have some so-called PL gen, or to generate your model, building information model, PL view to view your numerical model, the solver, and the post-processing to demonstrate the result. One of the good things is the post-processing data. You have it post-processing. You can zoom in with a lot of accuracy because you have continuous internal modeling. This is very simple slab with a beam, and this is the PL gen model. This is the model. This is a numerical model. Actually, you don't have points and lines, and this is the boundary elements. And I'm demonstrating here the beam and how the beam can get inside the column. You can simulate the partial fixed and the total fixed, and this is the very simple bending moment demonstration over the beam, and these are the boundary elements. You don't need to discretize inside for people with us. Here I'm demonstrating very simple problem most of us knew in civil engineering. This is called a slab beam type application, that the slab is carried over beams, and this is the same, but this is called beam paneled beam type. Paneled beam slab, because in the paneled beams are working as a stiffener for the slab. So the behavior of the slab is just a slab. The behavior of the slab and the beam is just a slab. Okay, and showing the dish shape only one. And here you can see the dish shape inside each cell here. This is very good for demonstration, for teaching purposes. Okay. Here I'm showing something, we published this in the ACI journal, I believe, and this is the only paper in the ACI journal talk about boundary elements. Even I was writing to them that they have to consider something in computational mechanics, because you talk about experimental only. You can see here, this is the shear stresses around the columns, and this is the demonstration of the shear stresses on lines. This is the linear stress hypothesis for the shear stresses. And this is, you can zoom in and see the shear stresses inside the column, around the column. This is very difficult to be done in finite element. It's even impossible without 3D finite elements. We have, as I said, the generator, the viewer, and the core manager, the solution, and the post-processing, and the design tool. If I look fast about the generator, it allows you to build your model, edit your model, and shows the boundary element division. You can define materials, any material you like. As I said, I'm going to leave all details in the presentation, so you can come back to it as a standalone document. You can define load cases. Here you can define load cases. You don't need to define at the moment combinations, because combinations will be defined in the post-processing. It's not like finite element software. You can define the model information, and this is very important point about the model information, is the beam, the column, you can take it as an area. We are not cheating. We are not showing the column as area, and it is not an area, it is a point. No, it is an area. The beam itself, with the actual size of the beam, even the first cell of the beam, you can control it in order to be able to model the transfer beam in the shear walls. Okay. Here, this is something called PL controls. PL controls allows you to modify the program day by day. I'm not going to talk about it because it's research-wise, because some of the controls that we have about 500 controls or something that is not used. We use this control day by day to improve our software. This is, you can start your building information model or your model using one of three ways. Either to draw your model direct on the interface, and you have drawing tools I'm going to show you. You have to, or you have to import your model from AutoCAD TXF model, or you can, this is, oh, sorry. This is, you can improve this from text file. You can write your model as text file. And this is very important because you can have other software, something like finite element-based software. You can use this text file as translator and you get in from here, or you can get it direct from DXF format. This is, I'm going to show you how to import your model from the DXF, and these are the tools. And this is to show the beam model. And here is a drawing environment. If you want to draw, you have grid, you have coordinates, you have everything. And these are the modes you have. And these are the elements you draw it at the beginning. You have a slab, you have supporting elements, you have loading elements, and all of them are not defined. Once you draw your elements, at the end of the day, you will define each element. Either it is a slab or opening, geometrical object, or you have loading element or supporting element. Here you select your tool and define your tool. As you can see, after the definition, these are the slab, these are column supporting area. We have something called wall assembly to join walls together. And I'm going to show you something. We have done it based on the formulation of Professor Casticadellis in warping. We join slabs together using vertical elements, just line elements, is not shell element, but we reach the same results as we joining as shell elements using warping wall, something we call it warping wall. And you can define drops, and drops are done here is in very intelligent trick. We published it in engineering analysis boundary ellipse. I'm going to talk not to talk about it today because I promised I'm not going to talk about mathematics today. Or you can define that the column is moving above or below the slab. Everything you can define it in this model. Once you have this, what you have to do is define your load cases. This is element by element definition about its properties. This is the columns, for example. This is the wall support. You have columns, you have wall support, you have soil support. And here now, the soil support, you can do it either Winkler, continuous spring under the slab. Continuous spring is not point spring. This is very important. Or you can divide it as elastic half space using Boussinesq or Mendelin solution. And if you have layering, you can you have all of type of layering, even the way of Steinbrenner approximation. It is based on colleague for Professor Castigadellis, Professor Stavridis. This is a soil support drops. You can define it. I leave all of the details here so anybody can come back to it. Wall assembly, if you have assembly of walls, as you can see, this is wall assembly. Even if you have very strange column shape in the plan, you can define this column shape with the actual area. And you can get exactly the straining action, and in the vicinity of the column, you can check of bunching. You can check of bunching around this column. And you will see we were able to check of bunching due to warping. And we published this also in engineering analysis. Here, the definition of the slab, this is the analytical model. Here is the analytical model. It is not a drawing. This is the analytical model. We don't have wireframe anymore. Okay, this is the definition for the beams. Here, I'm going to show you how the beams goes inside the column for the partial fixation or fixation. Even if you have beam just touched another beam, you can compute the torsion transfer or the moment transfer in this area, in this way. This is the definition of the column load, the loading elements. We have geometrical elements, slabs and opening, and you have loading elements and you have supporting elements. Wall load, load batch, wall and load assembly. If you have wall and load assembly, something like this is silo over pile draft, and we were able to model it. We have used this software in a lot of practical application here in the area of Egypt and North Africa and Gulf area. This is, for example, the silo problem. And here is the tools you have in the PL-BAC generator. You can match properties. For example, if you have the property for this file, you can match all other properties. You can draw array. It's the same like the drawing tools in any CAD tools or anything. This is the view, is a 3D view for OpenGL mode for your slab to check that you have done everything correct. You don't overlap anything with anything. At the end of the day, you can define your division. In the building information model, we start to move to the numerical model. With the numerical model, you define all of your divisions here, but it is written as a property of the object. Okay. Here, it shows the divisions also. We finished now. How can we generate our model? If we go to the view model, it is a numerical model now. With a numerical model, I'm going to show something very, very important. Just keep concentrating with me because I'm going to show something very important. This is a numerical modeling with different load cases. If you have different loads, it will show different in the 3 views. And all this is a toolbar you have. You can define the normal, you can define the direction of the boundary. It gives you the numbers of the boundary element and everything you have. You can zoom in, out, anything. And here is a numerical model you have. The most important thing I'm going to show now is this. This part, when I'm going to show you the support takes some sort of colors, as you can see. This colors tells you what are the group of stiffness you have. And this software is very, very important. You can define multiple stiffness supporting element. For example, if you have a plate supported on truss, you can do it. If you have a plate supported on very strange structure down to it, what you have to do is to define the stiffness, and it will be shown here. For example, here we have this area is an supporting area, supporting structure, and this is another supporting structure. Even you have circular column with circular area. We don't cheat. The circular column with circular area. In the numerical model, it's defined as circular area. And this is very important for files. You can show your result as in tabulated form also. Here, you can define all of the objects you have, like how many surfaces you have, how many objects you have. Here is, I'm showing that one of the beams here is not loaded with its own weight. This beams with own weight, and this beam is without own weight. It will show you also. This is the numerical model. If we go for the solution is done. I'm sorry, we have just internet connection. I'm back here now. Fady, can you come with me, please? احنا بنعمل ايه هنا؟ How can I share the screen? Okay. Fady is expert in doing this. Okay. So we are back now. I'm sorry for this, but we experience a lot of internet connection, but we will come back. It's not a problem. In the solution manager we have, وكده share. ده صح كده؟ The solution manager here, you can start to run one by one. كمان, you can sit down. We can run by load cases, and we have the several solvers. We have the normal solver, and we have GPU solver, and we have multiple core solution. For example, if you have here in Cairo University, we have very big server, and we run this using several cores. Is the solution. It shows you the case by case as a solution. The most important thing here, you can add your stiffness for the elastic half space. For example, if your raft is supported on elastic half space or supported on piles, you can link it to the elastic half space model and you can link it to the pile solution. Okay, or you can go direct to the design package. After the solution, you can go direct to the design package. So this before the solution and this is after the solution. Okay. After the solution, I'm going to demonstrate how can we show the results. You can first, before anything, you have to export some data from the model you have. For example, if you have wall assembly, this assembly has to be imported from the object itself in the model itself before we get the results for it. Because of that, we imported from the generator, and then this is for the wall assembly and for the beams. Then here we can define all assemblies here, and we can define also load combinations. Now the load combinations are defined in the post-processing stage. We don't define the load combination at the beginning. You can show the result as contour lines, rectangular contours or quadratic contours, or you can show strips, linear strips. Here I'm going to show the contours. This is the contour lines for the moment for the deflection. You can show the rectangle contours over area, and you can zoom in with. You can zoom in, for example, you can use 10 by 10 points, or you can use 100 by 100, you can use 1000 by 1000. Even you can have it very, very smooth. You can draw it on flat contour like this. This is very important to zoom in places where you have opening, when you have columns or something like this. Or you can have a point, pick a point and get the result at this point. This are the strips. You have a strip, you can have your result, any result you want. Moment shear, even in the moment in this direction. Even the design moment, you add the MXY according to wood armor equation. You can show the support results here as a pressure or as a total load. You can show the assembly result. For example, if you have multiple core load assembly core or something like that, you can demonstrate this assembly results, or you can demonstrate results on beams. You can have it. The design tool, I'm going to leave it for Ahmed Fady to represent it. Okay.
The design tool is a tool used the PL pack plate bend.
Again, we have internet connection. I'm sorry. Actually, we are using here two ways of the internet. So we are swapping. Once we have problem here, we swap to other ones. So continue.
The design package is to design the slab and the beam using 3 codes: ACI and Eurocode and Egyptian code of Prax, and there is applicability to add any other codes required. Okay, and not only it gives the design values, and also it gives calculation sheets in Excel format or spreadsheet format, and drawings, CAD drawings. Okay. Also, you can check bunching and check deflection
over irregular spans.
Yes.
Over irregular spans. This is very important.
Yes. This is show how to get the PL design from PL post if you are using PL post or for the core manager. Then we will talk in the design package in 7 items what the file needs to be exported from the model to use in the design, how to start the PL design, define the load combinations and the envelopes. You can design based on the envelopes, not only load combinations. Then we will talk about the design of slabs in 4 cases, and the check deflection, check bunching, and beam design. First, we export 3 main files. Export beam assemblies to read the assemblies of each beam in the from gen model to a PL design model. We export results file. We can save results from PL post and use it in the design, and export the assemblies file, as Professor Youssef said, for the assembly cores or assemblies supports. How to start the PL design? You can start the model you already designed before or a new model. In this window, you will choose your code There are 3 codes, as we said, and the parameters of the steel and the concrete. Okay, and to use the units, you will use it in the design, and also define the material properties you will use in the design. Okay? After that, you will define your load combination and load envelopes you will use. Slab design, you can say by 2 ways. I have already saved results from PL post and the design based on 2 methods, strip method or contour method, or haven't saved the data from PL post, so I will use the PL design to PL design, start from PL design directly and use 2 methods, basic and additional, which is common in the civil engineering design.
In Egypt, I don't know how in Europe what is
or strip-based design. So we will talk about these 4 methods. This is the strip already. It's saved from PL post. You can import it here in the PL design from results file you have already saved. Yes. After that, you will choose design slab, and from design slab to add strip to main model. After that, you choose add strip to this model. You define the 2 parts. The first part is the above part is for strip properties, the weights of the strip and which moment you will design based on it. And units.
You integrate the moment over. We don't use only one value. We integrate the moment to smooth it, and we put our reinforcement over the strip.
Exactly. And the second part in the bottom is to define the spans. Already the PL design automatically divides your strip into spans. In each spans, you will define the cover of the reinforcement concrete and the detailing, the details of the steel, number of bars and the diameters of bars and the alpha and the measure of bottom. And then you can use match properties to match the similar spans and other strips. Then he asks you if you want calculation sheets in Excel format or not.
This is the Excel format here, right? Yes.
This is the output Excel sheet format.
It gives you the code equation number.
Yes.
And the value in front of it.
Yes. After that, you will check the design that there is no errors and it's safe. If it's unsafe, you will increase the steel and repeat the same steps. After that, you can export a summary of this design data in only one Excel sheet. The second part is a design using contour design from already saved from PL post. The same, we draw contour on the PL post and then imported this contour to the PL design. After that, the same steps add strip to main model, but in this step, you will choose your saved contour data. Saved contour data, he will divide this area to 2 strips, strip in the X direction and another strip in the Y direction. You will define the properties of each strip in the above part here, and each strip is automatically divided to multiple spans. You will define each span as before. Same, you will start the slab design. He asked you if you want to export Excel sheet data for each span, for each strip, and you can export the design data, summarize it in only one Excel sheet. The third slab design method is directly by. Yes.
This is what I like, but people, they don't use it because you need to design several strips. Yes. But this area and additional one shot. But here this is the correct one actually.
Okay. PL design directly using strip base is the same as before, but here we choose create new region. There is no previously results. After you create your new region, just click this draw and you draw your what you want, which area you want to design. Okay, and there is 2 options: basic and additional, and strip based design. Here we will choose strip based design, and this region will automatically shown here. After you start the design, you will divide this.
Again, I'm sorry. Today, we don't know a series of interruptions.
Interruption. Here he divided the strip, the area you choosing, you draw to strips, strip in X and strip in Y, and each strip divided into spans. You define the same using match properties, define the spans and define.
Actually, we have to remind them that we kept all details to be standalone documents. Anybody come back to look at it, and we have series. We will upload a series of videos. We will upload it on the website.
Yeah. And after that, you can export the XF file contains these areas to the CAD, including its reinforcement details. The four methods, that basic and additional, it's common in Egypt. You can create new region and draw this region and define in the first part the main mesh. The main mesh, the main basic steel you add it in the two directions, top and bottom, and in the bottom part it's the additional you require. You will define that, and after you solve the blue parts is the safe bending moment due to the basic additional you added, and the red parts that exceeded the moment of resistance of your mesh, so you need additional in these areas. You will draw additional areas and solve and start the build design and exporting data, summarize it, or DXF file as we used. Now we will talk about check of deflection. We can check of deflection on strips, any drawing strips in the PL post. Here you will choose the major design parameter you want to check based on it, based on a bending moment or based on maximum deflection with right here and effective length, and this is
the idea here is the ACI code. It gives you on any other code the check of deflection based on simple spans. So if you have, for example, a very irregular flat slab, where is the span? So what we have to do is we draw the moment and we compute the point of inflection, because we have a smooth internal modeling. We compute the point of inflection. Actually, we use finite difference here. Once we compute the point of inflection here and the point of inflection here, this is the simple beam span. You need to check against according to the ACI code or any other.
Yeah. Also, you can check punching. Just we said before that we save assembly file. You import the assembly file. All the supporting elements appear here. You can check punching.
Check punching here is different, because what you have to do is you put your column, you put the area of the column, and you throw points, because punching is a brittle failure. If any one point fail, that means this punching is unsafe, and we published this. Even we wrote a paper about the theoretical basis of the ACI punching equation. Actually, after all of these years, boundary elements were able to prove the theoretical basis of the punching formula. Okay, and we extended this to include warping effect in punching. Here you can see a punching effect for regular column. You can't do this in any software you have. Okay.
This is a practical building.
Okay. The part, can you show them this? This is a punching calculation or two-way shear calculation. Even if you have beam, sometimes you fail in the two-way shear in the slabs, and this is very important. And actually, I sent all of this to the ACI committee of punching committee, shear committee. Okay.
Yes. Now we will talk about how to design the beams. Design the beam in PL packs. Divide the beam to two parts. The first part in the above part is called breaks, and this section called section design. The breaks at the support location, and the sections in between. If these beams is divided to breaks and these sections, this X is the breaks and the supporting elements, and the sections you define it to be designed. positive moment or negative moment. After that, each section you can add the properties, the cover, and the enforcement, and all this stuff data.
Actually, I don't like this stuff, but we are civil engineers. We have to do it. Actually, I like the mathematics part.
Yes. After that, you can use match properties for another sections. If you have a lot of sections, then you can export the design data for the beams and detailed Excel sheets using calculation and XF.
These drawings are generated directly from the software.
This is exported directly from BL design without any modifications. You can get this details from without any calculations, without any drawings on the CAD. Okay. Finally, we finished the BL design. We will go to the final part, last item in part 2 about PL back modeling capabilities.
I thought you would go to
PL back modeling capabilities. The main capabilities of the PL back that there is no longer domain meshing. You have the domain as it is. You can define the area supports and all elements, the actual geometry of the supporting element and loading element, and there is easy input. You can input using
multiple DXF or multiple text file. For example, if we have file draft, for example, you can assign a guy to draw the piles, and another guy to draw the slab, another guy to draw the loading elements. Once you have all of this, you can merge all of this together. You can merge all of this together using DXF, or you can merge this together using text document.
Yes.
Okay. Yes. And it's very easy to learn, I think. Yes. I think what you need for this basic package, what you need is 2 hours max.
Yes, because already draw the DXF as the real geometry. You didn't do any modification.
Actually, I have a student, he finished with me master degree. He used to get the laptop to the site and get some measurements and run the analysis directly.
Okay, and you can model a very, very thin, like small ducts opening. You can do it in the PL back. Okay, and
without the stress concentration.
Yes, you can model
track everything.
Also, the curved beams, all regular beams in the PL back.
Before we go, I guess you can add several stuff, but not from the interface, from the input file, like cracks or something like that.
Easy drawing, and you can model soil as a continuous spring, not a concentrated spring. Exporting and importing text file, post-processing, strip data and contour data can be exported to the Excel. Direct assembly of walls and cores, and save the results and restore the results after. Now we will go to part 3. Part 3 about one floor package.
We are going to change from our interface. Exactly.
Yes.
From our interface, instead of using our interface, we are going to use Revit interface. We know now Autodesk Revit, or the building information modeling era we have. So we embed our software here, as you can see. We embed our software here inside Revit, so we can use Revit directly. All engineers like Revit, so we will move now, instead of using the interface of our program, we'll use our program as solver. So we will use Revit interface. And now we will start with only one floor, then we will move to multiple floor and all building. Okay.
Yes. Through Revit PL back tool, you can add this in the Revit. And you can, this is several packages, as said before, tall building and foundation and all building and single floor exported. If you have overall building, you can export one floor, decided floor. From you draw in the Revit, you can export the PLGen automatically. You will not need to draw any data in the PLGen. Yes, it's automatically exported the PLGen. Just run the model and get your results in the PL post, and design it in the PL design, as we said before. Yes, and design your beams, and automatically after you finish the PL design, you can click one button and restore your reinforcement detailing to the Revit automatically.
Come back. So we
Yes.
go there for analysis and design, and come back to Revit for detailing and getting the drawings.
Yes, you go from export the model from the Revit and using the peel back and the design and restore the reinforcement automatically to the Revit again of the beams or
You can see
for
that
the slabs. Yes, the reinforcement of the slabs and additional areas you put it in the PL design.
Automatically, all of this done automatically.
Yes. Okay. We will go now for the foundation package. Also, foundation package, you can draw it from the PL Gen tool, as said before, or from the Revit. We will start with PL Gen. You can draw this pile draft with loading elements. All of this is the loading elements, and this is a 3 model.
These are the piles.
Yes, this is a pile, simpler pile.
Internal discretization. You can place the pile anywhere you like.
Yes. And this is the 3D model of the pile draft, and this is the loading elements. Then you go to the elastic half space window. In the elastic half space window, you model the soil as a continuum, not as a springs. You will define the layers of the soil as this is reported. In this elastic half space, you can use single layer, single infinite layer, or multi-layered using Farid or Powell's or equivalent spring method. And the theory you will use for the elastic half space, one of the 3, Mendelin or Boussinesq or Steinbrenner approximation. Okay, after using this elastic half space, you can export the stiffness of the soil. After that, if we have a pile, we go to the PP pack, which is a tool to calculate the pile interaction and the pile soil interaction effects. And from this, you just browse your input file. And
by the way, people in the literature they regard using Mendelin solution for half space or Mendelin solution for pile interaction as using boundary element method. Yes. But this is not a boundary element. This is analytical solutions.
After that, if in the pile editor, you can get the ID of each pile and define the nonlinear properties load set. Pile load test of each pile. I can here define
test from the
field.
Of the field.
Yes,
you can get the data and you put it.
Well, exactly. You can through this window. You can define for each pile its pile load test data, and after that run nonlinear analysis, and you will get nonlinear settlement or up to failure. You can load
for the building.
Yes, or also we will
say at the end of the day.
This is a load settlement curve of the pile draft up to failure or up to certain load. Here in the PL post, you can show which piles is failed and which piles didn't arrive its capacity. Okay. After that, you get the contours, nonlinear settlement, and the nonlinear bending moment based on this nonlinear analysis. Here you can draw your, we can move down to the basic information modeling.
Instead of our software interface, we can use Revit, the same for the foundation model.
Draw your raft, put your loads, the layers of the soil, the piles, all data is exported automatically. This is the analytical model in the Revit. You can export a text file, then it is the sequence, you can read it. After that, export text file and export gem files, and run the PL control, save, go to the elastic half space. All of this from with the wizard inside the Revit. You will not go to PL Gen or PL Post. All of this
this is what we call BIM center software.
Yeah.
Okay.
Loading the soil input data automatically exported from the Revit feedback, and importing the input file of the pile interaction already exported from Revit automatically, nonlinear data, and the run of the nonlinear analysis, and you can show the final reaction of the soil or the deflection on the raft or the bending moment. And
this is a huge raft, I guess. Huge raft is impossible to solve it.
Yes, we here demonstrate the rafts and the pile rafts. We already used PL back to solve it, and which is very practical, huge raft. This raft, you can imagine that these points, this black point, small black point, this is the columns. And these small lines, it is the shear walls. This raft is divided into 11 or 12 regions to be solved by finite element, and it's failed. And it's failed. And not, yes.
There is no connectivity.
Here you can use the PL back to solve it
Short.
within.
Actually, this is how
Yes, 300 meters in this direction and 260 in this direction.
Yes.
Okay, it's divided into zone. This is the zone of the zones. You can imagine that this is the column and this is the beams, and you can solve this raft. And this is a strip, one strip along this raft is the bending moment drawn on it, and the contours in each raft. You can only check punching on this raft.
You can check punching even if you have soil.
Yes, right? Yes. This is another building silos on the pile raft, and here we can show the bending moment inside the pile area, in the domain of the pile. This is another pile raft, pile caps connected with the beams, and we can solve this huge pile raft with beams. This is another pile draft. You can imagine this large circus is the piles, and these small points is the micro piles behind the regular piles. Okay, that's very, very difficult. Yes, we can enable this and solve this.
And with very few boundary elements, as you can see, very few boundary elements. In boundary elements, some people they say if I reach the correct answer with something like 200 by 400 finite element, we will use also 200 by 400 boundaries. No, not at all. What we need only is something like 10 by 20 or something like that. Yeah. Boundary elements. Boundary elements are very, very efficient in this.
Okay. In the foundation package also we do an iterative technique between the
either we can couple the superstructure with the substructure using iteratives, or we can do it directly. Here we publish this in the SCE journals for the iterative techniques. If you are interested in solving the superstructure using ETAPS software or something like that, but we can go direct for the overall building with our software.
Now we will go to part 4 about post-tension packages.
Post-tension is great in boundary. It's great. More than great, to be honest, in boundaries.
It's called PT-Pack, post-tension package. It's shear deformable plate tools. Also, we use ACI and Eurocode and Egyptian Code of Practice. And you can add any code instructions.
The best thing, it allows you to place the cables as you like.
Yes.
And according to the bending moment you have, what you have to do is just draw a strip. Near this strip, start to get the point of inflection and place your post-tension cables directly.
You have a 13 template for the profile of the cable. Okay, and you can do any load combination and envelopes. We start using PL design. We will talk about what the files you need to export, how to draw the cables data, the cables template, multiple cable selection, and how to solve using the PT-Pack and the check of stresses. You can draw the export from PLGen, export your model to text format, and then put the data in a folder, and then save the beam assembly data, or save the results from PL Post if you want. After you open the PT-Pack, he will ask you if you design reinforcement concrete slab or post-tension slab. If you choose reinforcement concrete slab, you will go to the regular PL design. If you choose post-tension slab, you will go to this module.
New interface we have.
Yes. This interface added some buttons here for the post-tension and this, drawing tools to draw this. This is a model. Yes. You can draw cables through DXF file. You can draw your cable profile in the DXF and import it automatically from DXF, or draw your cables here profile using this drawing tools, draw cable and array and snap points and all of this stuff.
Reminding you that all of this stuff using boundary elements.
Yeah.
Okay.
After that, you define the material properties and the divisions of the cable, the losses of the definitions, okay, and select each cable and you define its data, start and end cables. You can edit it and you jacking force, define jacking force, define losses, and define the template you will be used in each cable. This you have certain template with a different shape.
Design
Moment or the displacement shape, you can choose your template from certain template. Also, you can not edit cable by cable. You can choose multiple cables and define its properties in one shot. Okay. How to solve PT back? After you drop your profile cable, you can run PT back button. It will calculate the post tensioning cases. After that, he will go to the PL core manager and you will run as before. In the PL post, you can define load combination as we said before or envelopes. And after that, you solve it already the post tension slab. You can draw post tension strip here or any place in the slab. Okay. And after that, you can check this strip. You decide which moment, not in the X or Y direction only, you can in any direction, And you define number of sections and load combination and run this strip to get the top and bottom stresses. And after that, you can check your stresses. Okay. Now,
the post tension we have also we have optimizer.
Yeah.
You start your solution and it will work direct. It will give you the optimal solution.
Yeah.
Or if you have a ready-made from another software, we can import it here and we can make a value engineering for it.
Yes.
Okay. These are examples.
Yes, this is the practical example. Solve it using post PT.
You can see here. You can place your cable anywhere.
Anywhere. Yeah.
Okay.
And this is already post tension package like basic package. You can import it from Revit and the cables profile go to directly
to Revit for the details. You can see this is
a profile cable inside the slab in the Revit, and this is the plan of profile in the Revit of cables for the cables. This is a
demonstration. This is a video or something. I think we have to start. This is a video. I think
yes.
We
can show this video here, and this video show how to import the reinforcement data from post tension after I finished the PT pack solution and exported a text file contains the reinforcement. Just I choose this file and it's automatically imported here.
In Revit, you mean?
In Revit, yes. This is the Revit model I already exported to the BL PT pack. Yes, this is the cable already imported.
This is the overall building you have.
Yes. You can choose your floor to import these cables in it.
I knew it is a huge presentation because it is 8 packages. It's not only one package. It is 8 packages, and this is a work of about more than 20 years, to be honest, with a lot of colleagues here. But all of them believe in boundary elements.
This is a vertical elements reinforcement. This is the cables after imported in the Revit again.
I can see Professor GT Chan with us. I'm just welcoming Professor Chan with us. And I guess Professor Xing Hua with us also. I'm not sure. I don't have the total list of participants. So the one that appears to me is Professor GT Chan. I'm just saying hello to him.
When we go to the last part in this presentation, we will talk about another package, fixed base package. It's our building package. Okay, in the tool building package, it's BIM-centered software, as we said.
This is very important. Before. This is very important.
Yes.
Our idea is to make everything BIM-centered software. We start from Revit, go for analysis and design, and come back to Revit for details. You can see how boundary elements can help in civil engineering, because Professor Stavros Singlakis, I don't know whether he's with us or not, but he was asking me that this is something very strange to be done in civil engineering applications. No boundary elements can do anything, even in cosmology.
Yes, this software is a BIM-centered and lean process, and only one engineer
can do all of this.
Analysis and the design and reinforcement. And
the quantity. If you go for something, for a bit or something like that, you need to know the quantity, and in one day. Yeah. In one day, you solve a huge building using several combinations.
If we export the building only, it's called fixed base or tall building package. Or the overall, if we draw your raft and the pile draft and the soil data, we will talk first about fixed base. This is the wizard inside the Revit. You will export text files, and then data will export it automatically. Then we go to wall control to calculate warping functions and the post processing in the PL post and the PL view. After that,
is very important. If you look at this, is very important. If you look at Revit, it shows you the overall building, but our software, it is slab by slab. Okay, so we need to show the straining action over the vertical elements. So we developed a tool to demonstrate the 3D in OpenGL mode, and this is the tools.
Yes, this is a deformed shape of the building, and the straining action
come from our software. Yes. And this is comes with the straining action, with the bending moment, and
this in the PL pack forms. And this is the one vertical element design and the reinforcement of it. This is also a video. We defined how this is the 3D model.
The 3D model
pack. You can import, define load cases and the load combinations, and show the straining actions you want on the vertical.
The wireframe. This is a wireframe model, yes. But it is not a wireframe. This is just to demonstrate the straining actions.
And start the design of the vertical elements from this tool. Design of the cores. You can zoom in and zoom out and all of this stuff. This is the reinforcement of the core. After he finished the design in the OpenGL, or 3D PL back tool, he imported here the reinforcement to the model.
Back to Revit.
Yes. Open the Revit and imported the
design data. Yes, design data. And you can see the steel here direct.
Yes. Imported the text file of the design data of the columns of the cores. The log file is appear. Okay. Now this is the.
These are the reinforcement direct. Yes. You can see it
with the stirrups.
This is a real time video. Yes. Real time video.
Yes.
You can see here everything for the core.
Import. Okay.
You come back.
Here you can also use the PL design and the slab. Slab reinforcement with additional, and you can show here the connection between the slab and the walls with reinforcement, and all design drawings you can
details directly for you. Directly, you don't do it. Just Revit do it for you.
Design the beams, and this is the beams reinforcement exported automatically to Revit, and with the stirrups with everything. After that, you can from Revit, after you finished your design and reinforcement details, you can calculate your quantity of the reinforcement concrete. This is a huge building solved using the PL pack. Here we
the connection. You can have all type of connection. For example, if you have wall, then on this wall rested on two columns or the opposite or something like that, we made all combinations. It's embedded inside this wall.
This is a real building from 35 to 40 floors. Okay.
And this is a gen model here.
This is a Revit model, and this is a PLGen model. And this is a 3D PL back view and the comparison of some
between
the bound and finite elements.
The same.
Yes. This is an enforcement of the slab, and this is the drawing. You can get it detailed design drawings. You can take it from automatically from the Revit after your enforcement. And this is some cross sections from the Revit. Detailed. You didn't draw any of these sections. You already take it automatically. Okay. This is another building. We solved it already using PL back, and this is a comparison with the safe. This is a PL design. Yes, slab design and vertical elements reinforcement. All of these
are just showing the type of buildings we can use, what boundary elements can do in industry. I mean,
this is a design drawings
this is what engineers want.
Yeah,
and we give them.
And the engineers it take a long time to do these drawings. This is another real building.
This is a building we started at our presentation, and I told you I'm going to show you step by step how can we reach something like this.
This is the design, and this is some details about the core detailing, walls and detailing, and the column planted on a beam, and it's detailing. All this you can do it using PL back. We will go now for dynamic analysis. The PL back can solve dynamic analysis, including free vibration and time history analysis, including damping effects, and you can use it in the performance-based design.
Actually, we are implementing directly the performance-based design here. Yes. And we can also add
the number. Yes, this is the dynamic wizard inside the Revit code already. You can choose all the data. You can embed numbers in your building. This is
MR dampers. MR dampers in the code, and it solves.
This is the response.
And it can compute the optimum places of the MR dampers either to minimize the drift or to minimize the acceleration on the building according to the performance design you want.
This is the response before and after dampers. This is 9 floors. This is a real building.
The places of the dampers, as you can see.
The places of the dampers. There are.
And we already sent this paper for publication, actually.
Yes. Overall package, you can whole building, including the soil and the raft and the pile raft. This is you can solve it one shot without any substructuring,
including non-linear soil structure,
linear or non-linear soil structure interaction, including
the non-linearity here means you can go to the field, get the pile load test, put the pile load test inside the foundation package, and link it to the overall building, and it will sort out everything for you
using the stage of construction.
Even with stage of construction.
Yes. This is exported data of the overall building. You will get through the elastic hub space and the pile interaction and all of this stuff solved before, and you have the load settlement curve with non-linear analysis of the piles, and this is a 3D view in the PL back. This is a real building solving using overall, and this is a pile draft. And this is the design of the raft and supporting the raft detailing and the pile reinforcement. This is another building with different, here you can use different piles pattern and different shape of the raft to optimize the pile number of piles and optimize the piles data to get the optimum pile draft design. This is the pile reinforcement from the designed on the PL back 3D view and exported to the Revit. Finally, you can use this software in the constructions. You can, this is the time schedule of a project for a certain building, and on Excel or in Primavera, and link it to Naviswork. In the Naviswork, you can get this timetable and the construction stages 4D and 5D. Yes.
And you can see the construction of the building directly linked using movie. we can generate this movie direct.
Yes, we can generate this movie based on the results and based on reinforcement you already calculated using PLPAC.
And see the building is
Step by
being
step,
built
using the reinforcement. This is the
you
reinforcement.
can zoom in and see
Yes.
the reinforcement, everything. And actually, I was planning to have one colleague from computer science. We want to approve the building steel directly. What you have to do is to go there and take a photo from 3 places, and we use image recognition and pattern matching to be able to approve the reinforcement direct without sending engineers there and take a long time to do this. At the end of the day, now the presentation is finished. I have just one conclusion only. I always say you can do anything with boundary elements. And I really I got to be honest very upset when I meet a guy say no, we can't do this with boundaries. No, we can use everything with boundaries, and I'm demonstrating here what boundary elements can do in industry or civil engineering industry. I will open questions now. Let us see. For example, if we have in the chat room questions, just unmute yourself direct, ask us a question, and we willing and will be happy. We have Professor Shingwa, as I can see, with us, Professor J.T. Chan with us. I don't know who else with us. Professor Ashraf Ayub also with us. Professor, of course, Professor Castigadelis with us. Who else with us? I'm not sure. I can't see. Anyway, I'm ready for any question. Me and Dr. Fady, Professor Youssef. I'm ready for any question.
May I make a comment?
Definitely.
Yes. I have to congratulate you and your team, because you have turned the theoretical knowledge to engineering, practical analysis and design. I know that you work for many years, but you have converted all this theoretical knowledge, because there are people that say, "Oh, this is not. It has no practical application."
No, as you can see,
you can show. Yes, and for this reason, I have to congratulate you. You have continued the busy program, but the busy program used to solve more problems that were more general. You have applied to civil engineering analysis and praxis all this knowledge. Once more, I congratulate you and your team.
Thank you, Professor. I have to thank all of the team here. I have worked with several guys here, to be honest, and all of them, they believe in boundary elements. It's not just they are using boundary elements for master and PhD. We are believing in boundary elements. And I always say, when I look at you, I see your face. I see your boundary. So why I don't need to cut you to know you. Just I see your boundary. The photos we take is a boundary for you. Okay, even the stiffness method we study in the undergraduate structural analysis, it is actually boundary elements, because you get your solution at the nodes, and from the solution at the nodes you compute internal values. I don't know why people and they always say it is difficult, we need mathematics. No, it is now like a black box, and we give it to engineers, and we tackled all engineering problems. Post-tension slabs we solved, and I'm definitely sure within 1 year from now, post-tension slabs, it will be done with boundary elements. It's like fracture mechanics. Fracture mechanics now, boundary element is superiority in fracture mechanics. You have this location, you have displacement discontinuity, you have what we call it dual boundary, but I don't like this name. I like the use of structural equation, because dual boundary is different. I believe in post-tension slabs, in pile draft boundary elements is fantastic, fantastic. And even this software, you can implement your ideas in it. What you have to do is to generate your stiffness, and it will read any stiffness you have, or it can export the stiffness to your program or something like that. And even we are trying now to link it with one of the software, finite element based software in this aspect. I'm ready for any questions. And
just another small comment.
okay.
You see, in my lecture one day, 2 days before, you mentioned that you said that I didn't mention Dirac. Dirac
I see.
delta function.
You put Dirac.
Yes.
I can see.
You can see this is the most powerful idea, the Dirac delta function, and the fundamental solution. So it's something that the mathematicians think it is something quite theoretical. It has no use, but for us, it is the most useful tool in boundary integral equation method.
Definitely.
Okay.
Definitely.
Thank you very much. Thank you very much.
Thank you
for
Professor,
your
that you are with us. It's very important for us to see you. And actually, I was very happy to see you today.
Thank you.
Hazim Wasfi is raising hand. You can unmute yourself direct and speak direct.
Hello and good morning. Thank you very much for this great presentation, Dr. Youssef, Dr. Ahmed. Just wondering to ask about the time history analysis at the PLBAC. In the finite element method, we can assign the time history record at the joins or something along maybe the pile shaft. How can we do that in the PLBAC?
No, I can't hear Hazim. I can't hear Hazim. I can't hear. Can you say it again, please? But bit by bit. In finite, you do what?
Hello. In finite elements, we can assign the time history record at a point along the pile shaft. We
apply time history along the pile shaft?
Applying along the pile shaft. How can we do that in the PLBAC or in the boundary element method?
You can do this. You can do time history in anything. I recommend you to look at papers by Professor Banerjee. But he have done a lot of work for time history in piles. And I think Professor George Manolis, he did something in this. I believe so. Just there are a lot of papers, and you can embed this as far as you are using direct pile in a soil. But if you look at pile, a single pile as axisymmetric problem, we don't have this here in the PLBAC.
Okay, thank you so much, and congratulations of this great presentation.
Welcome. Any other question or any other thing? I'm ready for this. We have so many participants now. I welcome everybody from everywhere in the world. We have people from Brazil, we have people from China, we have people from Greece, we have people from England, and we have people from Egypt, several places in Egypt. So I'm welcome everybody. If there is any question or anything, we can have something like 1 hour. 1 hour, I think. Professor Xin Hua Xin will be with us talking about Traftys and fundamental solution-based finite elements. And this is alternative finite elements. Okay, we will see. We will come back after 1 hour, have a cup of coffee or something like that. I haven't done my coffee yet. And we will see you back in 1 hour time. Thank you, professors. Thank you, Professor Shing. Thank you, Professor Chan with us also. Thank you, everybody. Thank you, Professor Ashraf Ayub, and see you in 1 hour. See you in 1 hour. Bye now.